Welcome everyone to part 2 of the prediction profiler. We're going to be talking about the prediction profiler. And this week, what we want to do is really use that prediction model to make decisions, right? You're going to do a bunch of work, either the result of a DOE or building a prediction model from observational data. And now that you have that model, we're going to use the prediction profiler to make decisions. We're really going to find optimum conditions for the model. Now, last week we talked a little bit about exploring the opportunity space. Let's get on my journal here. So we talked about the default layout in the prediction profiler and about the basics about how to use the prediction profiler to understand your model. We also talked about the appearance, how to change some settings within the prediction profiler, and also how to share that with your colleagues. But today we're going to be talking about finding optimum conditions. And there's really two things that we want to find. We want to find optimum set points and optimum ranges for our inputs. And as we discussed last week, since we're talking about lots of different models that we can use with the prediction profiler, there's lots of different ways that we can talk about our X's or our inputs or our factors in our model, and our Y's, which are our responses and the output. Today, I'm going to be talking about a model generated from a DOE, specifically in the manufacturing space. So I'll be using terms like factors and response and set points and ranges. But just keep in mind that you can use the prediction profiler. You can do trade-off analysis for models that are built from observational data as well. All right, so we are going to be using the tire tread data. This is a sample data set, so if you want to take a look at it along with me, but it's called tire tread. And here's the data. So what we have in this data set is we essentially have 4 responses or 4 quality attributes associated with tires. And we've done a DOE on this process where we have these 3 inputs: silica, silane, and sulfur. And I'm just going to go ahead and run this script that comes in the sample data set, the RSM or the response surface model for those 4 responses. But this is essentially what we have. Let's just go right on down to the prediction profiler, right? Let's say that we've already refined our model, and this is our final model. Now, just as a reminder of what we have in the prediction profiler, we have a grid of graphs here. Each column on this grid is for each of the factors or the X's in our model. So we have one for silica, we have one for silane, and we have one for sulfur. Now we also have this desirability here, which is something new. And I'll get to that in a second. And then we also have the 4 responses. So across the rows, we have abrasion, modulus, elong, and hardness. So those are the 4 things that were measured in this DOE. Now, what we're going to be talking about is set points and ranges. So before I do anything, one thing I really like to do is know what these midpoints are. So you can see here with silica, silane, and sulfur, the default values are 1.2, 50, and 2.3 respectively. Now, JMP has just picked the mid-range of each of those factors. Again, if you have observational data that you've built a model from, JMP will display the mid-range of whatever is in that column for each of the inputs to your prediction model. So the first thing I'm going to do is remember these midpoints. So I'm going to go to my red triangle, and there is an option here under factor settings to remember settings. So I'm going to remember these settings as my my midpoints. All right, so what I see here are my midpoints. So the 1.2, the 50, the 2.3, and then the predicted response and the confidence interval for each of these responses. Now I also have these desirabilities over here. The reason I have these desirabilities, and let's go back to our data table. The reason I have desirabilities in my data table is because I have response limits associated with each of my responses. And if we come in here and take a look at our response limits, these are essentially a value that's been entered, so 100 to 200, and a goal. So I have a goal and a corresponding value. And the reason why these are in my data set is because when you design a DOE, so for example, let's go to the custom DOE platform. Whenever you enter a response, you enter in the goal for that response, and you can also enter limits. Now, these are not the spec limits, these are the response limits. And these response limits are used by the profiler. All right, these response limits are used by the profiler. And when we enter in our goal for our responses, we have the option to maximize, match target, minimize, or none. All right, so we have 4 different options. So I'm going to take a look at my column properties, or sorry, my columns manager, which is something new in JMP 18. That's really nice. And what I'm going to do is let's just look at our response values right now, our response columns. So here are our 4 columns for our responses. And you can see I have response limits for each of those columns. For abrasion and modulus, they're maximized, and the other 2 are targets. So different goals, 2 different goals for these 4 responses. So let's go back and take a look at our prediction profiler here. And that's why we have a different shape for each of these desirabilities, right? So we want to maximize abrasion. So desirability is essentially a number between 0 and 1, which will tell JMP what is the most desirable result for that response, right? So if we want to maximize, the lowest result is a 0, the highest result is a 1. If we want to match a target, you see we have a bell-shaped curve because the maximum response is somewhere in the middle of the range here. Now, I often get the question of, okay, well, when do I want to maximize, minimize, or match a target? And one way you can think of this is what type of specifications do you have on your responses? So this, again, is an example for manufacturing. So we may have specifications associated for each of these responses where we would throw away material if it was above and or below a certain level. So for example, let's come down here to manage limits, and let's enter in some specification limits for these process variables. So let's say for abrasion, I have a lower spec limit of 100, right? Because this is something we want to maximize. So you want to maximize a response when you just have a lower specification limit, right? You want to run your process as far away from that lower specification limit as possible. All right, let's say for modulus, we have a lower specification limit of 800. And then for the next 2, right, these are matched targets. So this is the case where you would have both a lower specification limit and an upper specification limit. So when you go to run your process, you want to run it down the center, right, in between your lower spec and your upper spec. So let's say for this, we have 400 to 600. And then also for hardness, let's say it's between 60 and 75. So just to show you here on my profiler, I'm going to come up here to redo and automatically recalc. And let's show those limits on these graphs, right? So here, now I have those specification limits displayed here on my graph. So I can see I have a lower specification limit for abrasion. So I want to maximize that, right? I wouldn't want to run my process down here right at the lower specification limit because again, I would get a predicted response right at my lower specification limit. And that predicted response is the mean. So that means if my process is running here down at my lower specification limit, 50% of the time I would be throwing away product. And the other 50% of the time it would be right above my lower specification limit. All right, same thing here for modulus. And for elongation, here's my lower and my upper specification limit. So I would want to match a target right here in the center. And for hardness, again, right, we want to try and target the center of my specification. All right, let me get rid of those limits just because the prediction profiler can get a little busy with those in. All right, so now that I have set those desirabilities, what I want to do is find the combination of set points, so the combination of silica, silane, and sulfur, that will simultaneously maximize my desirabilities for all 4 of my responses. So I want to find the combination of my 3 inputs that will maximize abrasion and modulus while targeting elong and hardness. So to do that, I'm going to come to the red triangle, go to optimization and desirability, and go to maximize desirabilities. And before I do anything else, I'm going to remember those settings because I want to have those saved somewhere. And so I'm going to call those maximize desirability, right? So here are my settings now. 1.25, 54, and 1.4 that maximizes abrasion and modulus while targeting my other 2. And you'll see here my desirability is 0.6, right? And if we come all the way over here to the right-hand side, my midpoints, my desirabilities was 0.008. So not a very desirable place to run my process in terms of maximizing desirabilities. And now we're better. We're at about a 0.6. All right, so that's one thing that we can do is maximize desirabilities. Well, you might say, you might go into this model now, and this is really where your subject matter expertise are going to come in, and really your opinions about your process, right? Because you might come in and say, well, abrasion is actually a lot more important to us than hitting these other specs. So abrasion's more important. So what can we do? Well, if I alt click, I'm on a PC, it's alt click. You might have to remind me where it is, what it is on a Mac. But if you alt click here on any of these desirabilities, you can change what is called this importance factor. So right now for abrasion, the importance factor is 0.25. So I am treating each of my responses as equally important. So they're all 0.25. But if abrasion was a lot more important in terms of hitting spec for whatever reason, I could change the relative importance of this. I can change the relative importance. And that's key. I'm going to say it one more time. You can change the relative importance because the exact number isn't super important. It's really the number relative to the other numbers, right? So the importance is 0.25 across all of my responses. So if abrasion, for example, was 4 times more important relatively to my other responses, I could change this to a 1. If abrasion was, say, 10 times more important, I could change this to a 2.5, right? So now with abrasion as more important than my other responses, I can go in and maximize desirabilities again. And before I look at anything, again, I want to save these out to this table below. So let's say abrasion importance was, let's see, we did 4x or 10x. I think I ended up doing 10x, right? All right, so we can see that there's been a little bit of change here in each one of my set points. But you can see for abrasion, we've gone from 109 to 120. So we're now operating a little bit further away from our lower spec limit, right? And again, just to remind you now, right, here's our lower spec limit for abrasion. So before, when we just maximize desirabilities while keeping everything the same, you know, we were operating at 109 on average. But when we say, okay, abrasion's a little bit more important, let's find the combination of set points that that maximize desirabilities while taking into consideration that abrasion is much more important than the other ones. Now you can see here we're operating a little bit more now farther away from our lower specification limit. Right, so that's another trade-off that you can think about when you're doing your when you're trying to find a set point, is which, if a response is more important than the other one. Another example of a response that might be more important, maybe you were taking cost into consideration while you were running your DOE. You could add a column for cost and have cost as a response here, and maybe you want to find the combination of set points that minimize the costs of the process. Right, so that's another example. Now, another common thing that may happen as you're doing your trade-off analysis is you may, you know, as a development scientist, you may go into the manufacturing department and say, okay, this is where we should run everything. And you can come in and round these, right? Silica at 1.1, silane at 51, and let's say sulfur at a 1.8. And, you know, maybe somebody comes in and says, you know, silane, that's still kind of towards the middle. We really need to run the process at a higher silane for whatever reason. Maybe the equipment performs better. Maybe there's other things in the processing of this manufacturing process where things run a little bit better. Well, in that case, what you can do is you can come in here. Let's change this to a 60. And let's lock that in. So I'm going to alt click anywhere within this column for the silane factor and lock that in. Right, so we're locked in at 60. Now my vertical dotted line is now solid. So silane is not going to change. So now we can find the combination of silica and sulfur that maximizes our desirabilities while keeping silane at 60. All right, so we'll go in, do that again. And again, before I do anything, I want to remember those settings. And so let's see, this is, we still have abrasion importance at 10x. And we have silane equals 60. All right, let's see, I'm going to remove this one here. All right, so now as we're going through and going through this decision process, we've remembered our settings here. So you can actually click each one of these radio buttons to take you back to each one of these combination of set points here that you've taken a look at. And it's important to notice, you know, what happens to the overall desirability. Well, there's trade-offs here, right? If we really want to run the process up there at 60, there is a decrease in desirability. And you can take a look and see how this impacts your predicted responses. Right, so we can come over here and see what our predicted response is and the confidence interval around this. And as we talked about last week, this predicted response would be the mean response. This is the confidence interval around the mean, right? So if you went out and went ahead and ran the process 100 times, this is what the mean response is. This is not what you would expect every result to be. This is the mean response. So again, one way that you can get a look at, okay, where would you expect actual results or individual results to occur? You can turn on your prediction interval to see what that interval is here. Let's turn off our confidence intervals. So we're just looking at our prediction intervals. So that gives you some idea of where you would expect individual results. But another question you may get is, okay, well, if we go in with these set points, what's our expected failure rate, right? We have a specification for each one of these responses. If we go in with these set points, what is the expected failure rate? Well, you can use simulation on this model to project your expected failure rate. And let's go ahead and use these set points here with silane locked in at 60. So we're going to turn on the simulator. And essentially what we're doing here is when we're simulating responses, we're going to expect some variability in our process, right? Every process has some variability. So with each run we do on our manufacturing process, we expect some variability from each, or there could potentially be variability from each one of these inputs. The variability could come from, I don't know, maybe if somebody is mixing this up by hand, there might be some variability that comes in there. If you're measuring silica with an assay, maybe the assay is introducing some variability as well. So let's go ahead and add some random variability here. And I'm going to go ahead and start simulating. All right. And essentially what's happening here is 10,000 runs are being simulated by injecting this variability here into the model. And it's saying here, this is our defect rate for each one of our responses. So we would expect about 16% failure from abrasion, about 0.5% from modulus, about 22 from elongation, and about 9% from hardness. The overall failure rate is 38%, right? And what we can do is we can simulate again, and you can see our numbers change a little bit, and you can kind of keep your eye on that number to see where it kind of dials into. So we're right around 38%, which is a lot of variability. Well, what's causing that variability? Well, it's where we're starting at. It's this variability we're injecting into our model. Well, where is this coming from? Well, JMP doesn't automatically know what the variability of your process is, right? It doesn't have a crystal ball to know what the standard deviation is for each one of these factors in your process. So what it does is it takes a look at the full factor range. So this, again, this data is coming from a DOE, so it's looking at that full range of each of the factors, dividing it by 5, and that's what it's using as your standard deviation. So 20% of the range. Again, if this was a model built from observational data, it would just take a look at the min and max in the column, divided by 5, and use that as standard deviation. Has to start somewhere, so that's where it's starting. You should probably, as a subject matter expert, you should probably have a better idea of what a better standard deviation would be to use in this case, right? So, if you've done maybe a study to understand overall process and assay variability, you might be able to use that, or if you've collected some historical data to better understand what your standard dev is here. This is also a good exercise to kind of know, to continue to do that what if, right? So, okay, failure rate is going to be really high if we go in with these set points. So again, you could change the set point. You could understand what reducing the variability in one of your inputs and how that would impact your overall failure rate. So that is also a nice tool here to kind of play that what if. If we were able to reduce variability in silane down to 3, cut that in half essentially, what's that going to do to our overall failure rate? Okay, so those are some great tools for understanding your set points and then understanding how those set points are going to impact failure rate. Now let's talk about ranges, right? So we've identified a specific set point, but sometimes you have to identify a range or a limit on your parameters of your process. So let's actually come back. Let's just go back to our midpoints. I'm going to remove this lock here on silane. All right, let's just uncheck that. And now let's look at our design space profiler. The design space profiler. This is where we're going to do to help set limits on our inputs, our X's, or your parameters, however you want to call them. So what do we have here? All right, so in the design space profiler, let me move this up so we're looking a little bit closer here at what we're looking at. So what we have is each of our factors. We have silica, silane, and sulfur. And what we're going to do is we're going to simulate 10,000 runs that fills in our entire factor space. So these were the ranges that we looked at in our DOE. So we're going to fill in that factor space evenly and take a look at what the resulting response is and whether or not we met spec. All right, so let's create, I always like to make and connect the random table here when we're talking about design space. So we're simulating 10,000 runs. We're adding in the random noise from each one of our runs, right? We're adding in random noise. And I'll just show you real quick where that random noise comes from. Here, if we take a look at our abrasion model, and here's our RMSE, that's our random noise, right? That's the error in our model. So that's where this error is coming from. So that's the noise going into here. So we've simulated 10,000 runs, and you can see in this data table, they're color-coded red or green. And they're color-coded red or green whether or not they've passed, or whether or not that simulated run would pass all specifications, right? So green means I've passed all 4 specifications. If I failed at least one of the 4 specifications, then it's going to be in red, right? So let's take a look at our design space or our factor space. I like to run the scatter plot matrix X. So here's our design space. So each observation, each marker in this scatter plot represents a simulated run, right? If it's red, it fails at least one specification. Green represents simulated runs that pass all specifications. So right now I'm looking at 100% of my factor space, and I'm failing 23% of the time. So about 23% of those points are red. Most of them are failing elongation here, right? Only 46% are in spec. So what I want to do is I want to set limits on my factors, right? So I can come in on that factor space to find where I have the highest probability of passing spec. So I have the option of either coming in on the low range of silica or decreasing the high point for silica, right? Same thing for silane. I could increase the lower end of my factor space or decrease the higher end. And same thing for sulfur. So as I move inward, this is a stepwise process here where each time I move inward, JMP is going to find the smallest change in my factor space that results in the highest increase in my inspec proportion. I'll say that again. JMP is going to find the smallest change in my factor space. So that change could be increasing on the lower end, decreasing on the higher end of any three of my factors, right? So the smallest change in my factor space that results in the biggest increase in my inspec proportion. All right, so I'm going to move inward once. I'm just going to click this once. And we've come in on silica. So let's go back out again. We're at about 2.0165. We're going to move inward. So we've made a small change in silica, and we've gone from 23.43 to about 24.6. And you can see over here in my factor space with my data table, I've now unselected those rows, right? So here's where I've unselected. So now my factor space is coming in. All right. So I can continue to move inward on my factor space. And there is actually another mastering JMP that we'll link below that talks about the design space profiler a little bit. But you can see I've only moved in on silica, right? It's just bringing things in on silica now. And now it's starting to bring things down on sulfur, right? So we're zooming in, not zooming in, but we're reducing our factor space to that area where we have the highest inspec proportion. And I'm keeping my eye here on my inspec proportion. We're up at about 65%. Really, I want to get up into that 80-90% range, right? At least. It depends on the process. But here, right, we're about 91% inspec proportion rate. Notice our sulfur range is really narrow. Our sulfur range is really narrow at this point. So there are, each time you're moving inward, you can think of the design space as being on a grid, right? So there's only certain increments you can move inward on your design space. So if one of your factors get really tight and maybe you have more precision, I think is the right term, if you have more precision to dial things in this space, you can come in here and reset your factor space. The number of grid points on each one of the factors is 21. Right, so you can make this narrower, which now takes those 21 points and distributes across the range at where you're at now. All right, so once you get to an inspec proportion rate where you're happy as the subject matter expert of your process, me coming from biologic pharmaceutical, I'd be pretty happy with this. Other people may not, so you'd probably want to continue to move inward. But now we have this range. This is now our design space, right? We took the entire factor space from our DOE and we've narrowed it into a design space. So we now have ranges on our process parameters that will give us the highest probability of passing spec. So now we can use these ranges, and we can actually take these ranges and send them to our profiler as constraints, right? So we're going to take this range, we're going to kick it back up to our profiler, and now we're constrained in on that range. We can also choose the midpoint of our range and send that to our profiler, right? So now we can choose to use that. I could use, remember those settings as well. Design space midpoint, right? And see where we are there. The other thing we can do, and let's see how we're doing on time. We're doing okay on time. The other thing we can do is use that range in our simulator. So I'm going to send those limits to my simulator and tell it, okay, we want the normal 3 sigma limits. And it's going to use that range now in our simulator to understand where we are, right? And so now we're down around 4% defect rate. All right, so that was Prediction Profiler to define your set points using optimized desirabilities. If you're going to go in with those set points, project your failure rate at those set points, and then using the design space profiler to understand ranges, to set limits on the ranges on your parameters, and then be able to use those to better understand what your projected failure rate is going to be.